Today, I'd like to talk about accountability for machine learning datasets. In particular, how we can learn from practices in software engineering and from technical infrastructure. To begin with, I'd like to consider some of the challenges that we face in accountability for machine learning data. And I'd like to acknowledge this trope that I think is fairly common in some of the discourse in machine learning, whereby the learning algorithm is seen as at worst neutral, but at best a positive kind of force. And any issues, harms, problems in the trained model are blamed on the data. And I think there are at least two ways in which we see data scapegoating in some of the fairness discourse, for example. We see arguments having the structure, the model is biased because the data is biased. Here, the data being seen as a direct antecedent for problems in the model. But we also see this second argument of the form, the data is biased because the model is biased. Here, using a form of pragmatic explanation, a form of abductive reasoning. That is, in the absence of any direct measurement of bias in the dataset, we use knowledge, evidence of bias in the model as evidence for bias in the data itself. And so these relate, I think, to what Nissenbaum has called the problem of scapegoating in computer systems, which she identifies as a challenge to accountability. And she writes here that human actions can be distanced from their causal impacts, while the computer becomes a direct causal antecedent. And in particular, with machine learning data, what we see is data mediating the interactions between models and dataset developers. We see dataset development work being distanced from its causal impacts on the model, whereas the data itself is seen as a more direct causal antecedent. And this relates, I think, to ways in which data work is undervalued within artificial intelligence. Sambi Saban has written, in Everyone Wants to Do the Model Work, Not the Data Work, about how data is often the least incentivized aspect of AI. Moller has written about how data work gets neither the necessary resources nor the proper compensation. And actually, this problem of undervaluing data work is not specific to machine learning. We see it in other fields of science too, for example, as discussed by Lane. And so one consequence of this undervaluing of labor is a distancing effect. Paolada has written about how machine learning's increased reliance on non-expert crowd workers tends to abstract away the human labor. And so abstraction being a cornerstone of computer science practice, here acting so as to distance labor from its outputs. And we see data workers naturally having lower status within the workplace as a result of all this. Moller has written about this lower status, and this is contrasted with the lionized work of building novel models, contrasted with the frequent discourse about AI superstars. Here meaning, of course, those who develop the learning algorithms, not the data. And we see phrases even such as deep learning savant in some of this savior discourse around AI. And so we see that machine learning's primary focus is on explaining differences between learning algorithms. And within this enterprise, datasets play the role of benchmarks. They are this fixed resource upon which learning algorithms compete. And so this reinforces data in the original meaning of the word, that meaning that of that which is fixed, that which is assumed, that which is given. And so we argue in the paper the relationship between accountability for data on the one hand, the visibility of the work that goes into creating data, the risks of distancing data work from the data that's generated, as identified by Nissenbaum as a challenge, and also the ways in which data work is devalued within the entire enterprise. These four are all connected to each other. A second challenge to accountability is what Nissenbaum calls bugs. And she writes of the risk of conceiving bugs as inevitable albeit unfortunate, consequences of a glorious new technologies. She writes, a more discerning approach to bugs would be to indicate a range of acceptable errors. Like focusing in here on this phrase, acceptable errors, requires some specification of which errors would be acceptable. Unfortunately, as Kuwajima has written, within machine learning, frequently we see a lack of clear requirement specification, as well as a lack actually of design specification. David Schlangen has written about the relationship between tasks, capabilities, and datasets, and how datasets exemplify tasks. And it's important to make this distinction between tasks and datasets, to make this distinction explicit, because if it's left implicit, we risk conflating the two. Datasets require verification and validation, which requires a clear specification of what the task is which they're exemplifying. And I think some of these issues we can see being played out in ImageNet in the last few years. So Crawford and Paglen pointed out a number of problems and issues with ImageNet, and we see in Young's response in which a number of maintenance tasks were addressed. One of the maintenance tasks was addressing non-visual concepts in ImageNet. And this raises the question straight away of why were there non-visual concepts in ImageNet in the first place? And why did it take so long for them to be removed? And to me, this suggests perhaps there was a lack of clarity around the original specifications of the entire task. A third challenge to accountability is that of many hands. As Nissenbaum writes, responsibility does not easily generalize to collective action. We see problems in datasets in this regard, not just in the ways in which data labor may be abstracted, not just in the ways in which the scraping or sourcing of data can obscure the hands involved, but also when we see dataset development teams which may have unclear divisions of responsibilities. And so before I get to some suggestions for mitigating some of these challenges, I first want to consider a couple of foundational questions, which I think suggest different paths forwards. The first question is, well, what kinds of things of datasets? How do we conceive of them ontologically? And the second question is, what kind of processes lead to their creation? Are these processes best thought of as art, science, craft, or engineering, or something else? So we argue in the paper that datasets can be thought of as technical infrastructure in a very real sense. Datasets have many of the typical properties of technical infrastructure. They're shared information delivery bases. They have well-defined architectures with standardized interfaces, just as infrastructure such as a railway uses standardization of a gauge to enable processes. Datasets enable new forms of processes that were not previously possible, but in doing so can actually make other processes more difficult, just in the way that a railway track can enable railway transport, but actually make cycling or walking more difficult. We see similarities in how infrastructure is evaluated and how datasets are evaluated. Infrastructure is evaluated based on its downstream uses. And when there is a one-to-many relationship between infrastructure and its users, we then have the problem of how do we assess and aggregate the value of those users, which are frequently distanced from the infrastructure development teams themselves. And in this challenges in evaluation, this leads to uncertainty in how to evaluate the infrastructure. And this uncertainty leads frequently to undervaluation. And this leads to some of the challenges we see with infrastructure frequently not being maintained because it's not being evaluated as much as it should, not being valued as much as it should. Datasets are also infrastructure in a second sense, that of the infrastructure study sense, in that they arrange how we view and structure knowledge in the world. Datasets define which tasks are possible and which tasks are priority, and which categories and structures of information are appropriate for addressing a task. We argue in the paper, based on this relationship with technical infrastructure, that dataset development is fundamentally a form of engineering. And we have 4 arguments in favor of this. Datasets are purposeful. They provide a means to do something. They acknowledge how, in contrast with science, which provides knowledge that. Secondly, engineering has this critical concept of a model, an engineering model, which is an abstracted, simplified model of reality, necessarily incomplete, yet nonetheless useful. And we argue that datasets are in fact prototypical engineering models. Thirdly, we draw parallels between the cultures of dataset work and those of software development, including influences by math culture, hacker culture, managerial culture, as well as engineering culture. And fourthly, we argue that dataset development is inherently nonlinear, that it defies deductive solutions. It typically requires reanalysis and redefinition, is often ill-structured or even wicked in nature. But despite dataset development being an engineering process, it is nevertheless also political. We need to acknowledge the impacts, the roles, stakes, expertise, objectives, and so on. And so Ben Green and Gina Neff have 2 great papers on this point. I'd now like to get to discussing documentation artifacts for dataset development and how they can assist in bringing visibility to data work and thus in assisting with the goal of accountability. So the typical account of accountability involves 3 phases. Information sharing, in which the actor shares information with the forum. This information is sometimes called accounts. And then the forum then deliberates and imposes consequences on the actor. So the question for dataset development is what accounts, what information are appropriate to share. And based on the arguments given earlier for thinking of dataset development as fundamentally engineering, the engineering development lifecycle provides a model here with stages of requirements, design, implementation, testing, and maintenance, each of which generate their own documentation artifacts. As noted earlier, Kuwajima has argued that machine learning is often characterized by lack of clear requirements and design. And we have found in discussions with machine learning researchers that often the distinction is even not well understood. But whereas requirements are critical in providing the ends, the design document describes the means to those ends, whereas requirements describes who will be impacted, who the stakeholders are. Design is about consideration of alternatives and validating the appropriateness of the solution. So once you have a requirement specification, you can then ask questions such as, were the requirements met? And are the errors that we see acceptable? Relating to Nissenbaum's point from earlier. We can also do adversarial testing on a data set. That is looking for maybe unanticipated, unforeseen, but possibly harmful artifacts that have ended up in the data set. And the last stage of the life cycle we consider is that of maintenance. And this stage is frequently undervalued, often overlooked, to the degree that we'd like to propose that, if you can't afford to maintain a data set, maybe you need to consider whether you can afford to create it. So we've argued that these 5 stages of the life cycle produce 5 distinct types of documentation, and that these documentation artifacts are natural accounts for the accountability process. That is information given to the forum for deliberation. We've argued that these 5 documents assist with the 3 challenges we outlined earlier, that by having clear ownership of the different stages of the life cycle can mitigate some of the challenges of having many hands by having clear responsibilities for the different hands. And by having a proximity of these owners to the documents and to each stage of work itself can help reduce some of the distance problems and thus some of the scapegoating risks that were described earlier. Lastly, as alluded to already, by having a clear requirement specification and by doing testing against those requirements means we can answer questions such as, are the errors acceptable? I'd like to finish now by by zooming out to consider some of the ecological challenges that would come to implementing some of these documentation practices, aiming at increasing visibility. First of all, we argue in the paper for the need to increase the recognition and valuation of expertise in AI data. Here we're echoing calls by Joe and Gebru for a subfield of AI dataset development with its own theory, its own practice, with venues for recognition, and with engagement with other fields of data disciplines. We argue that this is a critical step to increasing the visibility of the data work, because if you don't recognize the value of the dataset, people won't want to be associated. Secondly, we argue for more understanding of the processes of data work and for more investment in processes. Echoing Denton and Hanna, who also make this call for understanding the cultures and histories of dataset development. We have a greater need to understand the incentives and the disincentives for the various actors involved in data work. And some of the processes that most critically require more investment, I would argue, are processes of maintenance and technical debt reduction. As alluded to earlier, this is a common problem seen across many forms of infrastructure. Look at the decaying state of many kind of roads and bridges in many areas of the world. It's always exciting to build something new. It's not very glamorous to maintain it. So this is a persistent challenge and requires more investment. Lastly, we argue for more methodological clarity around machine learning in general. As alluded to earlier, there's often a lack of clarity around some of these methodological goals of machine learning. And we think that having more clarity about data requirements can actually improve the clarity around the goals of machine learning itself. Considering the painting shown on this slide, if the central figure is an anatomist aiming to learn about anatomy, if he's a surgeon aiming to fix a problem with this body, or if he's aiming to test the efficacy of a new form of scalpel, each of these has a role, but they have distinct goals, and their success needs to be evaluated in different ways. So we argue it's very important to distinguish the scientific and engineering goals of machine learning in order to understand how they relate to data. To summarize, we've argued for viewing dataset development as fundamentally a form of infrastructure engineering. We argue that by doing so reveals many similarities in the challenges for accountability that are also seen in the fields of infrastructure and engineering. We've argued for this relationship between accountability, visibility, proximity of data work to its outputs, and also for the valuation of data work. And so accountability for infrastructure requires consideration of things such as stakeholders, requirements, design, evaluation, and maintenance. We've argued that the typical engineering lifecycle provides a useful model for developing documentation artifacts, which provide useful accounts throughout the accountability process. And throughout all of this, we've argued that increased valuation of data work is a key aspect to increasing visibility and therefore accountability. Thank you.